Hi everyone, my name is Razan Jaber, a PhD student at Stockholm University, working with STIR Group. I'm presenting our research, Cross-Modal Repair, Gaze and Speech Interaction for List Advancement, that I have done together with my co-author, Donald Macmillan. Today, people can talk to speech agents' devices to search for movies, present instructions from a cooking recipe, or turn devices on or off. However, when people interact with speech agents, they usually come with a set of expectations far from the practical realities of use. In real use, there is often overlapping speech and less clearly spoken commands that could cause speech technologies to fail. As a result, users of voice interface technology become frustrated and can fail to learn the full capabilities of the technology or abandon use altogether. When the speech agent fails, people usually work to adapt their communication patterns to the needs of the system. People shorten their sentences, repeat themselves, increase volume, and hyper-articulate in attempts to be understood by voice interfaces. This has motivated our work to explore how users proceed to recover from common failures to overcome common speech interaction problems using multimodal interaction when advanced in a list of instructions. The hypotheses that guided our work are: users will be able to advance through a list of instructions by giving visual attention to the agent as fluently as using verbal instructions, and switching modality to affect a recovery will take longer and cause more frustration compared to staying with the same modality. We have conducted a Wizard of Oz study with 12 participants. Subjects were instructed to build a simple Lego tower in a series of spoken numbered steps by a smart agent, advancing the list of instructions on what blocks to add using either speech or gaze. The agent was designed to fail at specific points when providing the instruction to the user. During each condition, users were faced with the problem of recovering from failures. There were 3 error interactions induced, up to a total of 5 times, in which the agent either repeated the previous utterance or produced an error noise until the participant changed the way in which they attempted to advance the list, either changing modalities from gaze to speech or reformulating the spoken command. The study was conducted using the Tama Smart Speaker platform. Tama platform is capable of both speech interaction and gaze input and output. It uses a retractable spherical head containing 2 full-color LED eyes with 180 degrees of movement laterally and 60 degrees vertically to provide gaze feedback. This platform was extended with a browser-based Wizard of Oz control panel, allowing a researcher to control eye movements and color, and define and control utterances to be spoken by the text-to-speech system. We collected 3 types of data: video recording of users' interactions with the system logs of actions and interactions, and the SASSI questionnaire answers for each condition. For every participant, we acquired a log of what was said and what was recognized by the system for both gaze and speech condition. Each interaction was time-stamped, transcribed, and coded depending on its condition and the outcome of the interaction. For each interaction, we looked at the length of time taken to complete the building steps. In examining the interactions with the speech agent, the length of time taken to complete the building steps was used as a proxy for success. As we can see here in the tables, successful interaction with the system takes less time due to the lack of hesitation and repetitions. In total, there were 340 successful interactions included from the 10 recorded tests. Speech and gaze advancement worked equally well in terms of user experience and speed of interaction. When the interaction went smoothly, there was no significant difference between the gaze and speech condition. This result supports the hypothesis that taking advantage of cued gaze to advance through a list of instructions with a speech agent is a viable interaction strategy. When looking at the problematic interactions, there was 30 errors in total induced in the 10 trials for each condition. From looking at the table, we can see that users took longer time to recover from errors in the speech conditions than in the gaze condition. However, there was no significant difference between the time taken to complete the interactions in the gaze and speech conditions overall. When looking at the successfully recovered interactions, we found that there is a statistically significant difference between the speech and gaze condition, indicating that these interactions were shorter in the gaze condition than in the speech condition. This disproved our initial hypothesis that changing modality from gaze to speech would take longer than staying with the same modality and reformulating the spoken command. In order to understand why this happened, we examined the videos of how the participants recovered from the errors in the interaction. Looking closer at the transcripts of switching modalities interaction, we can see in this example, the participants switch modalities to advance through the list. The flow of interaction worked well. The participant notices that there is a repetition happening the first time the command is repeated, triggers another repetition with gaze, which she doesn't act upon, then verbalized the command next. Of the 11 participant videos analyzed, 7 interacted with the system in this way when their gaze failed to advance the list as expected. The result of the video analysis of the interactions showed the complexities of possible spoken repair strategies. As we can see in the transcript, the participant attempted to recover from the third error he encountered. After the error tune, the participant over-enunciates the same command in the first 2 attempts, first slightly, then with more emphasis on N in next step. When this fails, the participant opts for lengthening the utterance and attempts, "What is the next step?" and adds, "Please," asking, "Do you understand?" and getting a standard reply. The participant then reformulates to match the wizard's criteria with the command, "Go to step 15." The SASSI questionnaire result shows the mean and standard deviation for each measurement for speech and gaze conditions. Gaze was evaluated as better in all factors, except for speed. However, the t-test confirmed that these differences were not significant in any of the factors. This indicates that participants have received interaction with speech and gaze similarly in all types of interactions, for both successful interactions and those in which we induced failure. In conclusion, the quantitative analysis and the video analysis of the interaction and repair strategies carried out by our participants showed the complexities of possible spoken repair strategies as opposed to the relative simplicity of a switching modality, and the challenges of effectively communicating the meaning behind errors experienced when interacting with CUIs. Thank you for listening.